Welcome back to College Algebra. Let's see. So today's subject is especially intricate as far as these things go. It's very heavily algebraic, and like I said, it's relatively intricate. What we're going to be trying to do is starting with that definition of logarithms, where it was just a convenience thing. Now we have a way to write what's the solution to an equation like 4 to the x equals 5. If I write that, then of course x is log base 4 of 5. So I haven't done any real mathematics here. I haven't created any new information, but I've got a different format to write the same fact in that isolates x. And that's handy to have. But what we discovered last class was that previously we had said we're going to rewrite this in log form. But this time, since logs and exponents are inverse functions, I could do something else. I could say 4 to the x equals 5, and now, I could say 4 to the x equals 5, and then if I take the log base 4 as a function of both sides, so now I'm treating it like a function instead of like notation, and now I have log base 4 of 4 to the x equals log base 4 of 5. And we know that log base 4 of 4 to the x, these are inverse functions. Inverse functions. So they're going to cancel out, and we just have x on this side. So now that we know about inverse functions, and now that we know that logs and exponents are inverse functions, we have a new way of thinking about this same process. Instead of saying I'm rewriting this using new notation, I can say I'm applying a function to both sides, and now we have these two functions cancel out because they're inverses, and now we have this form, and now it's more like an algebra rule than like a change in notation. So it's a different way of conceiving of things, but it's going to help us out a lot today, because now if we know that logs and exponents are two sides of the same coin, and facts about one should translate somehow to facts about the other, since they're paired up as inverse functions. This inverse function pairing is really powerful, because when you have the graph of an exponential function, that graph tells you everything there is to know about the function. Like there's no property of the exponential functions that we couldn't discover from careful looking at the graph, because the graph includes every point on the function. And what I said is that to get an inverse function, you just need to mirror over this line y equals x, because that switches the x and the y coordinates. And the idea of an inverse function is you're undoing the other one, so you're switching the x and y coordinates. So then if I draw the log function, it's just the mirror over that line. But that means that, so this first function was, I don't know, we could say e to the x maybe, and this function is, we could say natural log of x. So that's another way to write log base e, so those are inverse functions. What I'm saying is, if every property of the function is determined by the graph, and we don't have any freedom in making this new graph, it's entirely determined by this mirror. So what I'm trying to say is that every property of this function should show up in the mirror image and vice versa. Everything there is to know about logarithms can be deduced from properties of exponents. So when we had all those fancy exponent properties, like, write these down here, we had a few fancy exponent properties like, if I have a base to the power of m times a base to the power of n, I can add the exponents. And if instead they were divided, I could subtract the exponents. And if they were nested, I can multiply the exponents. Properties like this are going to translate directly to the language of logarithms, because if this is a property that exponents have to have, and we discovered in Unit 1 that these are properties where as soon as I say exponents are repeated multiplication, these were inevitable. They were waiting in the wings for us to find, because as soon as I say exponents are repeated multiplication, these properties have to be true of anything that I could call repeated multiplication. Because I'm just saying if I have m copies of b and n copies of b all multiplied together, then I have n plus m copies of b multiplied together. So this property is inherent in the idea of this function. And what that means is that it's got to somehow be inherent in the idea of this function, since it's a mirror image of that one. So since these are inherent properties of exponential functions, any exponential function b to the x has these properties, well, now I know that log base b of x has to have properties that mirror these somehow. So today is all about finding those mirror properties and seeing what we can do with them. One of these properties, I think I mentioned to you last class, it's the mirror image of this one here. And it was the reason that logarithms were originally invented. It's a way to multiply large numbers together without having to do a whole lot of scratch work. So that's where we're going today. It's a little bit of a daunting task, but if you practice them, with enough practice, they get to be sort of self-explanatory. With enough practice, these properties we're about to learn, you will absorb them and you will be able to use them a lot faster than you currently think possible. So it's just a matter of practice once we've discovered them. Right. Does anyone have any questions so far? All right. So before we tackle that goal, I would just like to do a little review. So if I ask for something like log base 3 of 1/9, I need to find out what power of 3, what exponent do I have to take 3 up to turn it into 1/9. And once you've done enough of these, you'll be able to look at the base, look at the argument, and say, oh, I know the answer. I know what process gets from here to here. See if they'll show up from here to here. But in the meantime, what we can always do is say, well, let's say that's a for answer. So I'll rewrite this in exponent form. I know 3 to the power of a is 1/9. And then I start working out, how can I write 1/9 as a power of 3? And I know that that 9 down there is a 3 squared. And I know when I take 1 divided by something, that's the same as that something, in this case 3 squared, to the power of -1. And I know since I have nested exponents here that this is 3 to the -2, because that's 2 times -1. So that tells me that a is -2. And you can follow this process for any logarithm problem. So if I say what is log base root 2, so the base is a square root of 2, which is a little weird. The argument, let's say, is not 13. That's not going to work. How about 16? If this is the case, then again, I can tackle it with roughly the same method. I'd say root 2 to the power of a equals 16. And you always kind of want to get rid of radicals. So I'm going to say this is 2 to the power of 1/2 to the power of a. It's better to have just exponents, is what I'm trying to say. So we switched from logs to exponents in the first step. We're switching from this radical to an exponent in the next step. And since the left-hand side is written as a power of 2, I think it'd be convenient to write the right-hand side as a power of 2. So 16 is 2 to the 4th. And now I use nested exponents, and I say 2 to the power of 1/2 a is 2 to the 4th. And that means 1/2 a must be equal to 4. And so a can be 8. And now we know root 2 to the 8th power should be 16. So log base root 2 of 16 should be 8. So I just wanted to review that real quick before we jump into this new material. Any questions about evaluating logs before we go on? All right. So here's how the rest of this hour is going to go. I want to discover now these 4 advanced log properties. So we're going to get into a kind of a cyclic rhythm. We're going to make some machinery to develop one of these properties. Then we'll practice with the property, see different, we'll see different problem types that we can solve with the property. These give rise to some of my favorite problems in this class, just because the solutions I just think are really fun. So just as a reminder one more time, we're going to be finding, since these are inherent properties of exponents, and the natural log or any log function is completely determined by its mirror exponential function, by its inverse function, we should be able to come up with mirror images of these properties for the logarithm. So I'm going to start with this first one that I have underlined here. Multiplication outside the exponential function turns into addition inside the exponential function. And I want to think a little bit about how this is going to turn into a log property. Excuse me. I'm multiplying on the left-hand side. These are the outputs of the same exponential function at 2 different points. I put an input of m and an input of n, and then I multiplied the outputs together. Now on the right-hand side, I have one exponential function, and I'm adding the 2 inputs together. So copy this back down here. Add b to the m times b to the n equals b to the n plus m. And for the exponential function, I have multiplied outputs is somehow exactly the same thing as added inputs. And this isn't very mysterious because we know, once again, that m copies of b times n copies of b. Well, altogether, I have m plus n copies of b. So it makes sense that multiplied outputs are added inputs for this function. When we think of it in terms of notation, it becomes very clear why that's the case. But since logarithms switch the inputs and outputs, I would expect it to be true that for logarithms, if I add the outputs, that should be the same somehow as multiplying the inputs. This should go the other way around. Multiplied inputs should get me added outputs for a logarithm. So I'm going to try to prove that that's true. What I'm going to need are some dummy variables. So what I'm going to say is, let's say that we have this correspondence between these 5 letters. Suppose that b to the m is equal to x, and suppose that b to the n is equal to y. So I have these 2, and we're going to let this be our starting point for all of these proofs. So I'm going to say, suppose b to the m is x, suppose n is y, and I can rewrite these in log form. This means that log base b of x must be m. This means that log base b of y must be n. And now please feel free to raise your hand and stop me at any point during this procedure, because I want to make sure everyone's following along. So for now, though, I'm essentially just declaring my variables. I'm going to say, let's suppose that we have some variables with these correspondences. I just need names for everything so that I can refer to any part of these correspondences during the following proof. And here's what I'm going to do. I'm expecting multiplied inputs to turn into added outputs. So I'm going to go ahead and multiply my inputs. I'm going to ask, what is log base b of x times y? And we're going to try to use nothing but these 4 declarations to try to tease this apart. So there's going to be a lot of substitution. I'm going to use these 2 facts x is b to the m and y is b to the n. So I'm going to replace those in this expression. If I have multiplied inputs, and this is why I named everything. Now I can say x is b to the m and y is b to the n. So I've substituted these two top equations. And again, these didn't come from anywhere. I just said, hey, let's say x is the name for b to the m power, and let's say y is the name for b to the n power, and let's see where that gets us, you know? And so that directly leads to these two expressions because, well, if b to the m is x, then log base b of x is m. So then when I multiply these inputs, I have another name for them that's going to let me make progress, because now I've got b to the m times b to the n, like I have up here. So at this point, if I'm going to get a property of logs that mirrors this exponential property, I'm going to have to plug the exponential property in at some point. Otherwise, I'm not going to be able to get the log property out. So I'm going to feed this equation this property and say, well, b to the m times b to the n, which is, again, what we have right here, is equal to b to the m plus n. And so I'm going to replace it with that. So this is log base b of b to the m plus n. And now, as a matter of fact, we're almost done, because if I have log base b of b to the m plus n, I took the input m plus n, I stuck it in an exponential function, and then I put that output right back into its inverse function. Those are going to cancel each other out, and we just get our input back. So this is just m plus n. With this expression, I'm asking, what power do I have to raise b up to get b to the m plus n? And of course, that answer is you have to raise it to the power of m plus n. And so we're almost done here, because I know what m is, it's log base b of x, and I know what n is, it's log base b of y. So I'm going to put things back in terms of x and y now. M is log base b of x, and n is log base b of y. And so if we take a look at the first step and the last step here, what we just found out is that if I put the product of x and y inside the logarithm, that's the same as if I put them in their own separate logarithms and added the outputs. Just as I predicted at the beginning, if I have added outputs, I get multiplied inputs, because logs are the inverse of exponential functions. So the log base b of x times y is equal to the log base b of x plus the log base b of y. And this is the first of our 4 advanced log properties. I'll refer to this one as the product property. Does anyone have any questions on what we just did? This was a very high-level shenanigan. I just pulled every step as a substitution. So we did substitutions. Each equal sign is a new substitution. We did 4 of them. First, we used our definitions. Then we used our exponent property. Then we used inverse functions. And then we used our definitions one more time. So I had to invoke the exponent property from here to here. And I had to invoke the idea that logs and exponents are inverses from here to here. And when I put those 2 pieces of information together, it almost feels like transmutation. If I invoke this is a property of exponents in this step, and then logs are the inverses of exponents in this step, then what I get is a property of logs that mirrors this property of exponents. Just the way that those seem to, it almost feels like alchemy in a way. Like you throw those 2 things into the cauldron and then this is what comes out. For me, that's very, very satisfying. So I was hopefully, if you were following along at home, hopefully you find that satisfying too. Like I said last class, the reason that logs were invented, logs exist because Napier was his name, mathematician in the 1600s, got tired of multiplying big numbers over and over, and so he invented logs specifically to invoke this property. Believe it or not, before logarithms, they had been trying to do something similar with trig functions, but it only gave approximate answers. This gives exact answers. What he would do is if he wanted to multiply x and y, he wouldn't. Instead, he would go to his book where he had computed a whole bunch of logarithms. He would find the logarithm for x, find the logarithm for y, add them together, and look up that new number in his book. And he would find that it was the logarithm of whatever. So like if he wanted to multiply, maybe he wanted to multiply 4,100. Let me do this in a different color here. Maybe he wanted to multiply, so this is Napier's idea. He invented logs because he knew that if he could come up with the inverse function of exponents, that it would have this property. So if he wanted to multiply something like 4,096 times 312, he wouldn't. He would go to his book and he would go to whatever page 312 was on and write down its logarithm. And let me look that up real quick. 312. I'm going to do a natural logarithm. I don't know which base he used originally, but I would look in my book and say the natural log of 312. Because since b is the base here, this will work for any base as long as we keep the same base. So I'm going to use natural log since they're my favorite. The natural log of 312, Napier might find out that that was 5.743. And then he would go back into his book and ask what's the natural log of 4,096. And it turns out that that is 8.317. And then he would just add these two numbers together. He wasn't really interested in multiplying these by hand, but adding by hand is a lot easier than multiplying by hand. So I got 14.060. And now we're going to go into our book and ask 14.060 equals the natural log of what number? And so he'd scroll down in his book, and it's going to probably take him a little while to find that number. He's going to have to turn a lot of pages, but it's still faster than multiplying big numbers by hand if you have a lot of them, because eventually you're going to get used to the book in a major way. And I'm getting 14.060. Actually, what I did to look this up was I took e to the power of both sides, because this would say e to the 14.060 is just whatever that number was. Come on. There we go. 14.060 is the natural log of the number. Log base e of my mystery is 14.06. So if I take e to the power of the answer, I get the argument. I'm rewriting this log expression as an exponential expression. And my calculator is giving me the number 1,276,969. And so Napier would say, I don't think that's exactly correct, but that's pretty close to the right answer. It's good enough for an estimate. We could have used more decimal places if we wanted to get closer. As a matter of fact, the true answer for 4,096 times 3.1, or not 3.12, 312. Let's see, 4,096 times 312. Turns out that the true answer is 1,277,952. So sadly, I was off by almost 1,000, but that's what I deserve for only using 3 decimal places. I should have used 5 or 6 decimal places, and then I would have the exact answer. Well, either way, this was the principle behind Napier's invention. Because I don't really want to say discovery for this one, because Napier was like, I want the opposite of this property. I want the opposite of this property right here so that I can multiply my inputs and get added outputs. That's going to be really useful to multiply. And so he invented this log function out of whole cloth. I mean, it was always going to be there as a natural consequence. Like, it couldn't have been any other way, but he said, let's pull this out of the ether and use it to solve these problems. And so that was Napier's invention. Now, of course, today we have electronic calculators, and so multiplying is just phenomenally more easy than it ever was before. I could just type these into a machine and the machine will give me the answer. I don't know whether Napier would have loved that or hated it, but he's been dead for 400 years, so I guess it doesn't really matter. Anyway, let me show you some of the problems that we're going to use this to solve in today's college algebra, because we don't really need Napier's multiplication method if we have calculators, but it is kind of neat as we're doing algebra to, excuse me. It is kind of neat as we're doing algebra to be able to manipulate logarithmic expressions at will. This is going to turn out to be very, very useful in future math classes if you take them. And otherwise, it'll be, well, very, very useful on the final for this class. So for example, here's a classic problem type. The split this logarithm apart into its component pieces. If I say log base 2 of 8x, again, what I'm thinking is this has multiplied inputs, so I could rewrite it with added outputs. So I'm going to look, where's the multiplication? And it's between the 8 and the x, right here. So if this is my problem, my solution would look something like, I want to simplify this as much as possible. So log base 2 of 8 times x multiplied inputs are the same as added outputs for logarithms. So this is the same as log base 2 of 8 plus log base 2 of x. Because again, my property is that log base b of xy is the same as log base b of x plus log base b of y. In some sense, what you're doing every time you use one of these properties is you're going to say, I need to match the expression I have to one of the sides of this equation. So here I'm going to say, well, let's say 2 is b, x can be x, and y can be 8. So then I'd have the log base 2 of x and the log base 2 of 8 added together on the other side. So you match what you've got up to the problem. You match what you've got in the problem, rather, up to one of the properties you know, and then substitute in the other side, and that should allow you to progress through the problem. So now we've rewritten this log of a product as the sum of two logs, and the payoff is we get to go one more step. Does anyone know what the log base 2 of 8 is? Well, I know that 2 to the power of 3 equals 8, so log base 2 of 8 has to be 3. So I can change this one more time and say this is just 3 plus the log base 2 of x. That's my final answer. That's as simple as we can get this. So that's kind of weird. The log base 2 of 8x is the same as 3 plus the log base 2 of x. It seems really fishy to me because this is a horizontal shrink on the function. See if I can draw this here. Log base 2 of 8x. So this is a horizontal shrink, so it's going to be really narrow and skinny for a while. As opposed to the original function, which would have been a lot wider. And so this is log base 2 of 8x. It's a horizontal shrink. But somehow that's the same. I'm expected to believe that that's the same as a vertical shift up by 3 units. Well, it doesn't matter whether I believe it or not. It's true. We've done the algebra to prove it's true. So I guess we're just going to have to live with the fact that somehow a horizontal shrink is the same as a vertical shift for this function. And if that isn't the weirdest symmetry you've seen this semester, I don't know what is. A horizontal shrink and a vertical shift do exactly the same thing. I'd actually encourage you, if you want to understand this better, one of the things you can always do is play with it. I'd recommend going to desmos.com and play around. Try plugging in each of these functions. Try changing some of the parameters. If this 8 was a 16, if we shrank by 16, what would we have to add to make the same shift? I'm sure you can work it out yourself, but I think that could be a fun exercise, is play around with these a little bit in Desmos. And that could go for any of these properties, just to try to see how a crazy symmetry like this would work on a graph. All right. Any questions on that example? All right. Oh, this is why I like in-person classes. I'm really glad that the three of you are following along, but I think we got questions more often when there were more people in class. Oh well, nothing to be done about it really. If you have an online class at 8 a.m., I guess a lot of people are going to sleep in. I'm glad that you folks came though. Please do, again, feel free to stop me at any point if you need me to. Here's another example. If I have the natural log of 5x, y, so I've got a big expression inside my natural log. And if I'm doing calculus with this expression, I really don't like having a multiplication of two variables stuck inside another function. That's going to be basically when you're taking a derivative, there's a rule for one function inside another called the chain rule. And there's a rule for when two things are multiplied together called the product rule, different product rule than this one. But using one and then the other is going to make for a tedious and probably unnecessarily complicated computation. So it would be great if before I try to do the calculus step on this function, it would be really handy if I could rewrite that multiplication as addition. Well, what I want to show with this example is I can treat the multiplication anyway. So I'm going to try to refer to this formula and say, okay, b is clearly e here because this is a log base e. Let's say that the first thing multiplied is the 5, and that's multiplied by the xy. So I could rewrite this as the natural log of 5 plus the natural log of xy. But I'm not done, because I've broken apart one multiplication into addition. But if I want to keep simplifying, I can keep going. This is the natural log of x times y. So now b is still e, again, because this is a log base e. ln is log base e. X is x, and y is y. That was pretty simple. So in this step, these are multiplied. And so the log 5 doesn't go anywhere. That's still going to hang out on the outside. But now this log xy is a log x plus a log y. When you're applying this property, remember you have to do kind of two things at the same time to make this property work. We're doing the multiplication turns into addition, and it goes from the inside to the outside. So it's two things. Multiplication on the inside of the log function is the same as addition on the outside of the log function. Multiplying inputs is the same as adding outputs. But what we're seeing from this example is we can chain this property together. I did the natural log of 5 times x times y, and that ended up being the same as the natural log of 5 plus the natural log of x plus the natural log of y. So in the future, we don't always need to apply this property one at a time. In the future, I can just say I have two multiplication signs inside. I can turn them both into addition outside. It'll take a little practice to get confident in when that's allowed to happen and when it's not allowed to happen. I'm not saying you should do this overnight. With the first few, I'd definitely encourage you to take your properties and go step by step as slow as you can. But by the time you're done with work, if you haven't gotten to the step where you can skip from here to here, I would recommend going into your online textbook and working a few problems from the end of there. Remember, it's sad that we can't meet in person, but I'm still offering the same thing I did before. if you want to do some problems from the end of this section in your textbook, send me a picture of your scratch paper and I will be happy to look over it for you and let you know how you're doing. So it's not instant feedback like My Open Math gives you, but I'm more than happy to look over your scratch work if you need more help. That's an especially good thing to bring to office hours. If you want a math teacher to like you, bring work that you've already worked to office hours and go over it together. It's a very good use of office hours time. Oh, I think I have one more example of this property anyway. Last class, I found the phenomenal fact that log base 6 of 2 plus log base 6 of 3, it turns out to be 1. And last class, the proof of this was convoluted and crazy. I took 6 to the power of both sides and then did some manipulation magic. And the reason I had to do all of that was that we didn't have this property yet. Go on, scroll. We didn't have this property yet. Now that we have this property, I guess I'm going to have to just copy it down here. I'm going to say this is log base b of x, and this is log base b of y. So here x is 2, y is 3, and b is 6. And I know that the product property gives me that is log base b of xy. So that means that up above, I can substitute that in. This is log base 6, fill in the blanks, log base 6 of 2 times 3, which is, of course, log base 6 of 6. And I know that 6 to the first power is how I get 6. So when I ask logarithm, what power do I have to raise 6 up to get a 6? Of course, the answer is 1. So now instead of that crazy convoluted proof I gave you last class that these two numbers really add up to 1 and not just something very close to 1 like we saw from a computation, now instead of that, I can just say, well, this is a direct consequence of using this property. This time I substituted it in for the right-hand side of the property and got the left side back. So we can use this property in either order. The property works in either direction, but remember, it's always going to be addition outside the log is multiplication inside the log. So we can turn addition outside into multiplication inside, or we can turn multiplication inside into addition outside. We can't turn like addition inside into multiplication outside. That's not a thing. That's what exponents do, not what logarithms do. But if you understand what I mean here, this is one direction and this is the other direction of this property. It's still addition outside is multiplication inside, but the difference is which one we had first and where we were trying to go. So those are some ways that you can use the product property. As you can see already, we can see it's pretty versatile. But we're going to complement it with 3 more properties, 2 of which are very similar. The 4th one is its own bag of tricks. But what I want to say next is I had this exponent property. If I take b to the m divided by b to the n, I'm taking n copies of b and getting rid of n copies of b. So what I should have left is m minus n copies of b. There it goes. M minus n copies of b. I mean, frankly, this is almost identical to the first exponent property we had. It's just division instead of multiplication over here, subtraction instead of addition over here. So you can see how that would play. What I'm going to do is I'm going to take those same definitions that helped us before to prove something, and we're going to invoke a very similar proof process to turn this exponent property into a log property. So once again, I'm going to say, let's suppose that b to the m was x, b to the n was y, defining my variables here. That would make log base b of x equal to m, and it would make log base b of y equal to n. I'm going to use all 4 of these, because what I'm going to say now is, well, if division outside the exponent was the same as subtraction inside the exponent, logs should be the opposite. Division inside the logarithm, so I'll start this proof with log base b of, how about x divided by y? This should be the same as log base b of x minus log base b of y, if we follow the pattern from the previous one. So let's make it happen. Steps are almost the same. First step, I'm going to invoke these two. So this is log base b of b to the m divided by b to the n. Second step, I'm going to throw my x property into the pot. So I know that log base, I'm not going to worry about the logarithm right now. I'm going to do my work inside the logarithm for a bit. B to the m over b to the n is b to the m minus n. Third thing I'm going to invoke is that log base b of x and b to the x are inverses. So if I'm going to turn this exponent property into a log property, that has to be true. So here goes my third invocation. I put m minus n in the input, I put it into one function, and then put that answer into the opposite function. So the functions cancel out, and I just get m minus n. And then the fourth thing I'll do is undo this original substitution. So m is log base b of x, and n is log base b of y. So exactly like the last proof, what we've got now is that if I have division inside the logarithm, that's the same as subtraction outside the logarithm. So it's it corresponds very closely to this product rule. We're going to call this the, if I say log base b of x divided by y equals log base b of x minus log base b of y. We've shown that it has to be true. So since this has to be true for any b, any x, and any y, as long as they're in the domain, we're going to call this the quotient property, just like the product property before it. And just like the product property before it, this gets us some useful ways to manipulate logarithms. It would have also let John Napier divide really big numbers having to do long division with his parchment and quill, so I'm sure he greatly appreciated this property as well. But what we're going to do with it. Any questions on this proof before I run a couple examples? Okay. Let's say I write log of x divided by 1,000. That's a fine expression right there. X divided by 1,000. Remember, when I don't abase, this is just a side note here, when I say log of x, I mean log base 10 of x. So this is a common log. When I don't write the base, I mean log base 10. But what I'm going to do is I'm going to say, okay, so b is the base 10, x is x, and it's 1,000 here. So I'm going to invoke my quotient property and switch this over to log base 10 of x minus log base 10 of 1,000. And since I know that 10 cubed is 1,000, that's the same piece of knowledge, just written in a different form as the piece of knowledge that log base 10 of 1,000 must be 3. So I've gone from log x divided by 1,000 to log x minus 3. Dividing by 1,000 on the inside was the same as subtracting 3 on the outside. So I did a horizontal stretch. This right here, if this doesn't impress upon you how slowly logarithms grow, I don't know what will. Play with this in Desmos a bit if you don't see it. I did a horizontal stretch by a factor of 1,000. So picture making the logarithm graph 1,000 times as wide. Making it 1,000 times as wide is the same as doing a vertical shift 3 units down. Or in other words, if we go 3 units up, that's the same as getting 1,000 times narrower. So it's kind of crazy how slowly it would have to grow for that to be true, but there it is. Log base 10 is a very, very slowly growing function. What else can I say? Here's a second example. If I had a property, and these examples I'm doing, these are going to be very similar to your homework and very similar to the test work you do. If I said natural log of e divided by 12, of course I can rewrite that as natural log of e minus natural log of 12. And as a matter of fact, I can go one step further. Natural log is the same as log base e, and I know that log base e of e is 1, because e to the first power is e. So natural log of e divided by 12 is the same as 1 minus the natural log of 12. That could be handy. Let's see. Need to get an approximate number here. 1.26. Interesting. Okay. One more example. If I did log base 3 of 12 minus log base 3 of 4, look at this and see if you can predict what this is going to be. We're going to use this quotient property again. Now we're going to use it in the other order. And if it helps, I could tell you that log base 3 of 4 is about 1.262. If I take 3 to the power of 1.262, I get 4. If I take 3 to the power of 2.262, I get 12. So I think you might be able to see from that what's going to happen here. I'm saying log base b of x minus the log base b of y is equal to the log base b of x divided by y. So up top, plugging in my numbers, this should be the log b is 3, x is 12, y is, 4. And of course, 12 divided by 4 is 3. And of course, the log base 3 of 3 is 1, because 3 to the first power is 3. So it turns out that these numbers really were exactly 1 apart, and that's because 12 is 3 times 4. So another way I like to think of this is that, you know how multiplication is repeated addition and division is repeated subtraction? The logarithm somehow breaks that down. If you put the repeated function inside the log, you get the unrepeated function outside the log. So multiplication inside is addition outside, division inside is subtraction outside, and as we're about to see, exponents inside turn out to be multiplication outside. So the logarithm powers down these arithmetic operations, in a sense. And that's why addition and subtraction inside a log don't go anywhere. There's nowhere lower for them to go. But multiplication gets turned into addition, division gets turned into subtraction, and the next one I'm about to show you is that exponents inside turn into multiplication outside. So the logarithm, again, is powering down these repeated operations. And that makes it really handy for people like Napier who would like a nice low power operation to do by hand. So here's our third. Oh, I still have a bit of ground to cover. Hope I get through this all today. I'm going to take these same definitions one more time. This time I don't need the y, but I'm going to talk about the idea that if I have b to the power of m, and then I raise that to the power of a, that's equal to b to the m times a. The nested exponents rule in exponent outside an exponent is the same as multiplication inside the exponent. So logs are going to go the other way. Logs are going to power an exponent inside down into multiplication outside. So again, I'm going to start with the assumption. Let's say x is log base b of m. No. I don't want that. I'm sorry. I'm going to say x is equal to b to the m, rather, so that m is log base b of x. That's going to get me what I want. And now I'm going to start with an exponent inside. So let's say that I start with the log base b of x to the power of a. And now we're going to follow the same 4 steps we did in the last 2 proofs. So these 4 steps again. We're going to follow those steps one more time. The first 3 properties I'm showing you today are all close cousins. They all power down operations. So we're going to do it again. I'm going to substitute in this b to the m. So this is equal to log base b of b to the m is x, and that's to the power of a. Next, I'm going to actually use my exponent property. These are nested exponents. If I have a copies of m copies of b, that's the same as having a times m copies of b. Whoops. So I'll use that property. This is log base b of b to the m a. And then I'm going to use the fact that these are inverse functions. So the b to the x and the log base b of x cancel out, and I've just got m times a. But I know what m is. M was log base b of x. So my final answer is this is a times log base b of x, because that's what m is. So in other words, log base b of x to the a, an exponent inside the log, is equal to a times log base b of x. It's multiplication outside the log. I call this the power property, if you need a name for it. Any questions here? Well, if not, what this lets us do is a couple of really fun problem types. Oh, this is good. This is good, because now I can do combined problems with the first 3 properties. This is really good. So these are the kinds of problems you will definitely see on tests and finals. If I had the log base 2 of, how about z to the power of 3 up top, and x and a y to the power of 5 down below. And I want to simplify this as much as possible. I want to break this expression up. I'm going to use all of my properties. First, I'm going to say I have division inside, and that's going to turn into subtraction outside. So I'm going to take apart this expression one piece at a time. And the biggest piece I see, the biggest joint holding this together, is this division sign right in the middle of the whole expression. So I'm going to break that up. This is equal to log base 2 of z cubed minus log base 2 of x times y to the 5th. So I've turned that division into subtraction. That's the quotient property. Now, I'm going to break this log base 2 of x times y to the 5th up, because there's a multiplication. That's the glue holding this one together. And take this multiplication dot and say that's addition outside. So this is log base 2 of x plus log base 2 of y to the 5th. And I'm being careful here because I am going to have to distribute this minus sign in a second, but that's more of a technicality than anything. In fact, let me do that right now. This is log base 2 of z cubed minus log base 2 of x minus log base 2 of y to the 5th power. We're almost done. We just used our first 2 properties, and now we're going to use our third property. An exponent inside the log is multiplication outside. So for example, I could take this format and say, my base b is 2, the x here is z, and a here is 3. So the 3 is going to come outside and everything else will be the same. The log base 2 of z cubed is the same as 3 times the log base 2 of z. The log base 2 of x stays put, and log base 2 of y to the fifth is 5 times log base 2 of y. So I have expanded this expression as much as possible. Instead of this nasty expression inside the log, I've got the simplest possible expressions inside the log now, single variables. This is going to be so much easier to do calculus with. If you're doing calculus on this, you are wasting your effort. You should break it into this form first and then do calculus on it. It'll save you a ton of time next semester. So that's expand the log problem. Of course, we can go in the other direction. If I want, I could take a broken up log expression and pack it all together by using all these properties in reverse. So if I said I'm going to start with 3 log A, and I have minus a half log B minus a half log C. Whoops, these are not the bases, these are the arguments. Since I'm not writing the bases, this is a log base 10, this is a common log. And now I want to go in the opposite direction. I want to glue this thing together as much as possible with my log properties. So the very first thing I'm going to do is put all of these coefficients inside as exponents. This is the log of a cubed. This is the log of b to the 1/2. And this is the log of c to the 1/2. Before I don't have a property that says 3 of this log minus half of that log is something inside, but I do have a property that says this log minus that log is something inside. And that's what I want. This is log of a cubed divided by b to the 1/2 minus log of c to the 1/2. And I'm going to do the same thing again. I'm going to also divide by this one. So I'm going to take this and also put it in the quotient here. So this is log of a cubed divided by b to the 1/2 and c to the 1/2. I don't really like the way I wrote that argument, so this last step is just a notation thing, no math happening here. But that would be log of a cubed divided by the square root of bc. And I think that's a lot prettier. It's b to the 1/2 times c to the 1/2 is the same as the square root of bc. So this is a nice, pretty way to pack this all together into one expression. And it just depends what your purpose is, which one of these you want to do. But I also want to point out, these are the kinds of problems, these 2 examples I've just done, we did them in 4 steps each just now. We applied our properties one at a time. We went slow and careful, and slow and steady wins the race, like the tortoise and Aesop's fables, right? But eventually we should try to keep this level of accuracy while going at the speed of the rabbit. In other words, once you've practiced enough, you'll be able to say, all right, z was in the numerator with a power of 3. So in the end, it's going to be a log of z with an exponent of 3. X was in the denominator, so the log of x will be negative. 5 was in the denominator with a power of 5, so I'll be subtracting 5 times the log base 2 of y, like so. Or over here, I say, A has a coefficient of positive 3, B and C have coefficients of negative 1. So I'm going to have an a cubed in the numerator, and I'm going to have a square root of b and a square root of c in the denominator. In other words, once you get how these 3 properties mesh together, the order of operations is exactly what you'd expect. I expect it'll be intuitive for you after you do tonight's homework. And so try to get to the point where you can jump from here to here in one step, because your future self will thank you so much for that if you take calculus. You'll be so glad you did. The fact that you can jump from here to here is going to cut like 10 minutes off of every calculus problem you do with logarithms. It'll be great. It'll be great. So for now, of course, it's fine to go step by step carefully, but in the end, you can go very, very quickly through these. That's another one of the reasons I think these log properties are so much fun. All right, looks like we have 15 minutes. So I suppose that's, woof. Yeah, Yeah, well, I do want to do this problem next. Here's a different kind of problem. I call it a mystery-based problem. I like these a lot. I'm going to give you a logarithm, and I'm not going to tell you what its base is. So I'm going to say log base b of 2 is about 0.356. I'm going to say log base b of 3 is about 0.565. But I'm not going to tell you what this base b is. And I'm going to say, if we assume these are true, I want you to find I want you to evaluate the value of log base b of 6, log base b of 36, log base b of maybe 2/9. Okay? So we know some values of the logs, and we're supposed to find other values of logs from them. And the way we're going to do that is by using log properties to make these arguments out of our original arguments. So for example, for log base b of 6, and this is a 6, not a b. So, whoops, that was too much. 36. There we go. If I want log base b of 6, I could say log base b of 6 well, 6 is 2 times 3, and I know that multiplication inside the log is addition outside. So this is log base b of 2 plus log base b of 3, which is 0.356 plus 0.565, and that's going to be 0.921. And there's my answer. So I didn't need to know what my base was to compute this answer. And that's a mystery-based problem. So we can use other log properties. I'll leave these two kind of as an exercise for the reader, but we can do this same kind of process to get these answers. And what I want to do is hold off on those for a little bit. If we have time, I'll come back at the end of class and do this. But I definitely want to get to the fourth log property before we go, and I'm not sure how much time I'll need for that, so I'll come back to that if there's time. Right now, I want to talk about this fourth property, and this fourth property is a really strange one, so just bear with me here. Let's suppose that, once more, let's suppose that b to the m equals x, and that means that m is log base b of x. This is going to be a bizarre one. There's not really an exponent property that comes along here, so what do I end up invoking? No, this one's weird. So, I said the first three properties were cousins. This one is not related to the first three, like the first three are related to each other. But it's useful in its own right. So, let's say that I took, instead of log base b, let's say I took log base a of b to the m. Now, I know that that is equal to log base a of x, because x is b to the m. But I also know that it's equal to, I can use the exponent property and say m comes outside. So I know that m times log base a of b equals log base a of x. I'm sorry, I don't have a roadmap for where we're going because, like I said, this one is just bizarre. What I'm going to do is solve for m. I'm going to put m by itself, and that means I have to divide log base a of x divided by log base a of b. But the payoff is I know what m is. I know that m is log base b of x. And this right here, this strange equation is known as the change of base property. And here's why it's important. A couple of reasons. There are a lot of calculators, mine included. I don't know about yours. It depends what calculator you got. But there are a lot of calculators that aren't going to let you type in log base 4 of 153. So on my calculator, I don't have a button for log base 4. I know that newer calculators sometimes do, but the old ones don't because they depend on the calculator's user knowing the change of base property. Here I'm going to say, let's say 4 is b, and let's say 153 is x. So what is a? Well, a isn't defined on the left side of the equation. A can be anything we want. Oh, a for anything. What if a is 10? Then this would be log base 10, x is 153, and this would be log base 10, b is 4. So what I'm saying is the log base 4 of 153 is the same as log of 153 divided by log of 4. So what we're doing is we're decomposing a log expression. The argument goes in the numerator, the base goes in the denominator. They both go inside logarithms, but we can pick the base of that new logarithm. So in this case, log base 10 of 153 turns out to be 2.184. Log base 10 of 4 turns out to be 0.602. These are both approximate, of course. And when we divide those, we get about 3.629. Now, was that, I said A could be anything, but that really, we almost have to suspend belief. Like, there's no way, right? If I said log base 4 of 153 and now I use, say, the natural log instead, log base e. Okay, yeah, I mean, what are we going to get here? The same answer? That'd be crazy. That'd be absolutely crazy. The natural log of 153 is 5.030. It's a completely different number. The natural log of 4 is 1.386. Not even close to the same. So I divide these, and the answer turns out to be 3.629. It's 3.629 again. It doesn't matter what base you pick, whether it's 10 or e or 7 or 1,000,002. You will get different numbers here, but their quotient, the ratio between them, will always be the same. And it'll always be equal to log base, the denominator base, of the argument. So this is a real cool way to split up logarithms. I just think it's neat. I just think it's neat. And it comes in handy in some of these decomposition problems too, like if I said, tell me what is ln x plus 2 ln y divided by ln of 4. I can do the numerator real quick. The numerator is ln x, and I'm not going to skip a step yet, but this is the sort of place where you would. Ln x plus ln y squared over ln 4, and that's the log of x times y squared over the log of 4. So I put the 2 inside with the power property. I put the x times y squared inside with the product property. And now this is a place where a lot of people get bamboozled and say, oh, there's a division that turns into subtraction. This division does not turn into subtraction. Subtraction outside the log is the same as division inside the log. Division outside the log is the change of base formula. Here, the numerator thingy is xy squared. The denominator b is 4, and the base a is e. That base a is going to go away. It doesn't show up on the left side of the equation. we just get log base b of x. So in this case, we just get log base 4 of x times y squared. It doesn't matter what the original base was. We get the same answer either way. So if every other step of this problem had been in terms of log base 6 instead of natural log, the final answer would still be log base 4 of xy squared. So like I said, this is a strange one, but it works. So, looks like we have 5 more minutes. Any questions here? If not, I do want to go back up and finish this problem then. We've got a little more time. So if I ask for log base b of 36, let's see. I want to do the same thing. Here's a shortcut. Was this the section? I can reduce this to a problem I've already solved, see? Log base b of 36 is the same as log base b of 6 squared. And I know what the log base b of 6 is. It's 0.921. Now I can pull the 2 outside with the exponent property. So it's going to be multiplied, not an exponent anymore. So we've powered the exponent down into multiplication. And I know from the previous step that log base b of 6 is 0.921. This is 1.842. Otherwise, I guess we could have written as 36 as 2 times 2 times 3 times 3, and then added 0.356 plus 0.356 plus 0.565 plus 0.565, and that would have gotten us the same answer. So we have options. As a matter of fact, the power property, the quotient property, and the product property, those 3 are such close cousins. They're really more siblings than cousins. They're interchangeable in a lot of problems, including this one. I could have done this all with the power property, or I could do it all with the product property. I could even probably come up with a dumb way to do it with the quotient property if you had a gun to my head. As a matter of fact, if I asked you for log base b of 2 divided by 9, well, first off, I know that I have a quotient in there, so I'm going to get rid of that right away. This is log base b of 2 minus log base b of 9. And I have log base b of 2. I know that that's 0.356, but I don't have a log base b of 9. Any ideas what I could do to get a log base b of 9? Well, this lesson's better when it's interactive, but since there's only 3 of you, I can't really fault you. If it were the 4 of us in person, we'd be interacting right now, but that's online teaching, I guess. This is log base b of, because I have a trick, you know, 9 is 3 times 3. My trick is, in person, I can always make eye contact with someone until they get so uncomfortable they answer my question. But here it's more like, we're all sitting in different buildings with headphones on. It's like, okay, well, can't really single anyone out to answer a question this way. Oh well, we got log base b of 3 times 3, which is log base b of 2 minus log b of 3 plus log b of 3. I didn't need to do this many steps to answer this question. Again, this is one of those cases where once you get proficient with the 3 log properties, you'll want to just jump ahead. But in the end, I get 0.356 minus 0.565 minus 0.565. And that turns out to be negative 0.774. So yeah, that's your log properties. So we have learned the 4 advanced log properties today. And these are going to be just indispensable as you're dealing with logarithms from here on out. They are incredibly helpful. What we have left to do in this unit is there's equations where we're going to take logs and exponents, put them in equations and try to solve those equations. And then we also have modeling, where we're going to try to do a bunch of different real-world problems. Now that we have all these advanced tools that we didn't have on day one, we're going to go back and really hammer inflation, radiation, interest, bacteria, viruses, all that kinds of stuff. We're going to be able to model those with these really handy properties we have now. We're going to have a lot of fun doing that. So that's what's coming up. Otherwise, thank you all so much for coming. Hopefully we can get more people next time, but oh well. It was good to see you all in here, and I guess I'll see you on Tuesday. So long.